relevance is what's important. So let's make this relevant to our industry. Here we go. Ohm's law can be stated this way: E equals IR. E, back in George Ohm's day, was electromechanical force, EMF. You hear counter EMF and all that kind of stuff. That's voltage, basically. We represent it today as V, small v, voltage. But back then, electromotive force was what they called it. I was intensity or inductance, and that's what we call amperage today. And R has always been resistance, and that is measured in ohms in simple circuits, DC circuits, not in AC circuits. So E, voltage, is equal to amperage times the resistance. That's essentially what we're saying. Now, you can extend this formula out as you can algebraically with any formula, E equals IR, or anything that E equals A times B, ends up the same way. The best way to remember Ohm's law, if you have to take a test, a NATE exam or a CM exam or a CSM exam, whenever I've taken any of those tests, what I do when I sit down, they always give you a piece of scrap paper. I sit down, I write E over IR, just like you see it here in a triangle, sometimes in a circle. But E is over I and R. Now, when I'm given a question and I have to solve for voltage, E, I cover it up in my mind, and what I have left is I times R. E equals I times R. So I multiply the amperage times the resistance they gave me, and I get the voltage. Sometimes they ask me to solve for resistance. So in my mind, I cover that up, and now I know I have to take the amperage and divide it into the voltage to get the resistance. You see how that works? This also works for three-phase power, but you got to multiply E, the voltage, by 1.73. 1.73 is the square root of 3. And the voltage in a three-phase circuit is not 240, it's 240 times 1.73. Caution: cannot apply Ohm's law for resistance to AC inductive loads. Inductive load is a motor. Anything that draws a higher amperage when it starts as opposed to when it runs, you can't apply Ohm's law. It doesn't work. Because inductance typically is associated with solenoids, coils, stator, rotor windings, that kind of thing. And what a coil is a source of magnetic energy. Because as you run current through there, you create a magnetic field around those conductors, that winding. That inductance actually opposes the flow of current through that actual wire. It opposes itself. And because of that, Ohm's law can't apply to any kind of inductive load. Because if you take any motor in your shelf, doesn't matter whether it's PSC or whatever, and read the volts times amps and do the math, you're not going to come out, when you put your ohm meter across the windings of that motor, it's going to come out nowhere near what Ohm's law is going to come out to, because your ohm meter has a battery in it. And it's sending voltage through that coil, and that voltage is generating a magnetic field which is opposing the flow of that battery current through that very coil you're testing. So it gets very funky, to say the least, but just remember, don't apply this Ohm's law to AC inductive loads. Resistive loads, fine. Electric heaters, that kind of thing, everything is fine, because those are non-inductive. An electric heater draws the same amperage, voltage, etc. when it starts as when it runs. There's no inductance. There's no surge of power. And we'll talk more about inductance later on, but get the broad strokes here of Ohm's law. So I write E over IR when I sit down. The other thing I do, in fact, let's talk about this right now. I didn't realize I put it in a section. Inductive and resistive loads. An inductive load is an AC electrical load in which the voltage wave reaches its peak before the current. Inductive loads use magnetic fields, such as motors, solenoids, etc. If it moves, it's probably an inductive load. Inductive loads use magnetic fields, okay? They're motors, they're solenoids. If there's any movement of a shaft or whatever, it's inductive. This is what it looks like. Here's a resistive load. Now look at this part of the sine wave. Here is, which is your voltage line? Here it is here. Voltage is here. This is amperage and this is power, okay? You see power, I, right here? What happens? They all peak at the same time. That's resistive. That's beautiful. There's no inductance here. Power, amperage, voltage, all peak at the same time. Take a look at this same circuit, but now we got a motor in here instead of some kind of resistor. Look at this wave now. Your voltage is back here peaking. This is, I believe, I. Yeah, here's your amperage peaking way after that. It's lagging, okay? And then your power is offset to the right. So this is inductive. This is why graphically Ohm's law can't be applied to an inductive load, and this is why graphically it can be, because everything's in line, just like a DC circuit. You'll also see contactors specified that way. You'll have this coil in this case, and this contactor is 120 volts. There's two poles, you know, two poles, okay? Full load amps is 30 amps, and the resistive load is 40 amps. You can take a higher resistive load because there's no inductance. You're not going to get that surge of voltage and current like you get in inductive loads. And they're going to happen at the same time, and it can handle it. 40 amps, no sweat. Hook it up to a heater that draws 40 amps, this contactor will be fine. Hook it up to a motor that draws 40 amps, and you're going to overload it. You're going to burn the contacts. It can only handle a 30 amp motor. So E over IR. The other thing I write down is pi. P over IE. Now a lot of the books will state it the other way. P equals E times I, not I times E. Me, it's easier to remember pi. And I need all the memory devices I can get. So, if I want to know P, which is power, okay, watts is power, and what is watts? Power is volts times amps. If I cover up P, I'm going to solve for P because I covered it up. I'm going to multiply the amperage times the voltage, or the voltage times the amperage. Doesn't matter which way you do it. You're going to get the same answer. You're going to get watts. If I cover up amperage and I know the wattage and the voltage, I'm going to divide the voltage into the wattage and get the amperage. Works the same way the other one does. Three-phase, you can use this, no problem. Multiply voltage by 1.73 if you're going to apply Ohm's law. The voltage times 1.73 divided into the three-phase wattage will give you the amperage, or the amperage you should have. There's a thing called power factor. If you want to know the true power, you have to multiply the volts times the amps times the power factor. Remember that, let's get past this for a second. Remember that 1 watt is equal to 3.413 BTUs of heat. If you generate 1 watt, you generate 3.413 BTUs. If you have 1,000 watts, a kilowatt, 1 kilowatt is 1,000 watts, K is killi, okay? So you then have 3,413 BTUs. Now you know how hot a light bulb gets when you try to change it right after it burnt out. If the light bulb was lit a few minutes ago and you go to grab it to pull it out, it's going to burn your hand because a 100-watt light bulb is going to be generating about, what, 34.13 BTUs. No, I'm sorry, 341.3 BTUs. I didn't move the decimal point correctly. 100-watt light bulb. That's hot. 341 BTUs. A match is about 1,000 BTUs. So 300 is a third of a match. That's pretty hot, a wooden match. Power factor. You got, if you want to know the true power, you got to multiply volts times amps times the power factor. Power factor is the ratio of real power to apparent power. Real power is the actual power being used by a circuit. Apparent power is derived from Ohm's law when you read volts times amps. So let me cut to the chase here. Here's your resistive circuit again. The power factor here is 1 because everything peaks at the same time. However, in this inductive load, we don't have that. Our power factor is going to be something less than 1.0. And how do we determine that? We determine that by the simple way to do it in the field: take a watt meter out, hook it up appropriately, read the reading. The watt meter is going to give you the real power, the actual power being used. Then disconnect the watt meter, hook up your voltmeter right where you took the watt meter readings, read the voltage, read the amperage there while the unit's running obviously, and multiply voltage times amperage and divide that into the watt reading, and that will tell you how efficient that circuit is. Because this is the standard efficiency formula. If you want to know how efficient something is, divide the output by the input. Take a gas furnace. If it's 80,000 BTU output and 100,000 input, you divide the output by the input, you're going to get the percentage of efficiency. If you divide 80,000 by 100,000, you're going to get 0.8 or 80% efficient. And that's what we're doing here. We're saying this is the actual wattage we get from a watt meter reading, and this is the voltage I read times the amperage I read, which essentially is Ohm's law, and I divide this into that. This is my input, that is my output. Okay. That's what power factor is. Let's apply this. Ohm's law is real interesting and all that jazz, but let's have some use for it. Electric hot water heater, heating element. 240 volt, non-simultaneous operation, which means that both of them never operate at the same time. They're non-simultaneous, okay, and the thermostats make sure of that. They're 240 volt, 4,500 watt. 4,500 over 4,500. Very, very common. 50, 70, 80 gallon, whatever it is, hot water heaters. So what should the amp draw and the resistance be when measured across a good element? Okay, a good element. What should it show up as? Well, P over IE. We're going to solve for power. We know that it's 4,500 watts over 240 volts. So volts divided by watts is going to give me 18.75 amps. So if this heater is good and I hook up my amp probe to the element, split the wires, hook up my amp probe to one of the elements, that's exactly what I should read. Or something very close to that. Your meter is going to do a little rounding, but that's about all. Now, that tells us what the amp draw should be. What should the resistance be? If I hook up my meter here and it beeps, does that tell me that the it makes a noise, or the needle deflects one way or the other? Does that tell me that this element has continuity? It can't, because that element is surrounded by water. If the element were wide open, you'd still show continuity on your meter, but you wouldn't show the correct continuity. The correct continuity should be about 12, 13 ohms. How do I know that? I took the voltage, E, divided it by the amperage, we calculated 18.75, divide that into this, I get this, 12.8. So if I read 2 ohms, guess what? I get a short. I get an open element that's shorted through the water to ground. Series circuits. Let's look at series circuits. Let's revisit this. Remember, series is the Christmas tree lights. In this case, I'm showing you a AC power source. This is a plug in the wall. That's what that bad symbol is there. That's the sine wave. And in series, I have a 10 ohm resistor in this case. It could be a 10 ohm load of some kind, 20 ohm, and a 30 ohm. The voltage is divided across each of the different resistances. Across this 10 ohm resistance, I'm going to have 20 volts, because you use E times IR. Across this 20 ohm resistance, I'm going to have 40 volt drop if I measure my voltmeter from here to here. And across this, I'm going to have a 60 volt drop. But if I add them all up, they add up to the supply voltage. And they drop according to their resistances. If they were all the same resistance, you would have exactly the same voltage drop across them, and in this case it would be 1/3 of this. Okay, so you'd have a 40-volt drop across each of them, and that would add up. 3 times 40 is 120. That's what voltage does in a series circuit. Current, the total current flows through each of the resistances. So no matter where I read the current, if I put my ammeter here, 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 there, doesn't matter, I'm going to read the same thing. In this case, 2 amps. I got a total of 60 ohms divided into 120 volts gives me 2 amps. The resistances are added together to get the total resistance. Here's the formula mathematically. The total resistance in a series circuit is resistance 1 plus resistance 2 plus resistance 3. So I have 10, 20, and 30. That adds up to 60 ohms. That's the way a series circuit works. AC loads, because of what we just saw, should never be placed in series. If you place 2 AC loads in series, these are 2 loads, 2 coils I hooked up to here, 2 solenoid coils, each 24 volts. I got a 24 volt transformer and I got a 24 volt thermostat. So if the thermostat is closed, I have a power source, an uninterrupted path through both of the loads. I have loads, so I have a useful circuit, and I have a destination. What I don't have is the proper voltage, because when I close the thermostat, these 2 are going to sit there and go because they're both the same. They both have the same resistance. I have 24 volts available. I put them in series, and the result of that is each of them sees half of that voltage. So this 24 volt coil is never going to pull in with 12 volts. Any more than a 120 volt motor will run on 60 volts. It'll attempt to. It'll make a lot of smoke and a lot of humming, but it ain't going to turn. This is what happens when you put loads in series. Go ahead and put light bulbs in series. No big deal. You can put switches in series because they're not loads, but you can't put loads in series, especially in AC circuits. You just reduce the voltage to each of the loads. If I put a third one of these in series, I'd end up with, 1/3 of 24 going to each of them. Each would have 8 volts then. They would hum a little less and you get more smoke out of everything.